Thank you for the introduction. Again, I'm Bryce.
And I'm Ruben. We work at Twitter on Finagle, which is a RPC library that we use extensively across our microservices. It encodes tons of best practices that the industry has learned and that we've learned along the way for doing RPC at scale. Today, we're actually going to focus on one of the components within Finagle. Its core component, the load balancer.
All right. Specifically, we're going to tell you about the evolution of Twitter's client-side load balancing. We're going to tell you about a few of the algorithms we've used in the past and the trade-offs they make. And then we're going to tell you a little bit about what we're doing now and our current thinking about load balancing. So we're going to start off with telling you about a balancer called P2C. And it's a balancer we've used extensively at Twitter, and we still do in many places. And it's nice because it is both simple and fair. Then we're going to tell you about how it doesn't scale as well as we need to in some situations. So we've come up with another one that we term aperture, or more specifically, random aperture. And then about the trade-off that it makes, namely that we trade fair for efficient. And then finally, we're going to tell you about how we've been able to refine random aperture into what we call deterministic aperture. And this is a load balancer that regains the fairness of P2C while even improving on the efficiency of random aperture.
So in modern serving systems, you're going to see load balancing at multiple layers in the call graph. We're going to be focusing specifically on service-to-service load balancing. So this is load balancing between services. And why do we actually need load balancing there? What does it buy us? So in the context of a service-oriented architecture, as soon as you scale horizontally, you need a way to manage and distribute load across your replicas. And in order to safely make use of our replicas, we need to front them with a load balancer. Another important feature of application load balancing is failure management. So we know that both hardware and software can fail. Since all requests to a service are now flowing through a load balancer, it's well positioned to manage that failure of replicas when they do fail. So let's break down some of the terms that we use to describe our load balancers. We say that they're non-cooperative. So we have multiple load balancers, each making decisions independently. And this allows us to not incur any heavyweight coordination. We say that they're client-side. So we embed each load balancer inside a client, and we do this so we can operate with fewer layers of physical infrastructure. When we say load balancing, we mean load balancing over both sessions and requests. So session distribution is an important metric that we use because sessions are a vehicle for requests, but we mostly measure the effectiveness of our load balancers via request distribution. And that's because request distribution is a more accurate proxy for server resource utilization. So let's take a look at an example. Here we have service A talking to service B. So each instance of service A has an embedded load balancer. Each instance of service B has an equal number of sessions, in this case 3, because each load balancer in service A is opening up a session to all remote instances. In other words, all clients are connecting to all servers. So given this topology, how do we balance requests?
We use a strategy we call P2C. This is based on the seminal work of Michael Metzenmacher in his paper titled The Power of Two Choices in Randomized Load Balancing. This is a very simple and elegant algorithm, and it starts off by service A needs to, an instance of service A needs to dispatch a request. So it picks two instances of service B, and it simply picks the best of those two, and that's who gets the request. So this is the implementation of that algorithm in Scala, and as you can see, there's not a lot of code. And I think it's worth going through it for a second and breaking it down into the interesting pieces. So the first bit is where we select our two nodes. As you can see, it's just pick a random integer in the range. Do that for each one. Line 5 is just to make sure that we don't accidentally pick the same node twice. And then we have our nodes. So after we have our nodes, we then evaluate each node's status. So status is just a notion we have in Finagle that's easily comparable. It's a roll-up of stuff such as circuit breakers, the node's health, its history, and it just allows us to compare whether one has been marked down for other reasons. In the common case, they will both be open, and then if so, we fall to line 16, where we evaluate their load and simply take the least loaded of those two nodes. So let's recap what we get from this. The first thing we get is a fair request distribution. As is outlined in the paper, we can expect a request distribution to be that is exponentially better than simply picking one node at random and sending it to there. And this comes from the load comparison phase. So we also see that it's efficient, namely that all the operations are done in constant time and they're fully concurrent. We don't have a data structure that is required to keep track of the current load of every request and response pair. And lastly, we've been able to, it allows us to decouple selection and comparison. Seems kind of silly, but it's actually very powerful, because in the previous slide, we didn't actually tell you what load is. There could be many sophisticated definitions of load, and if we had coupled the two, then they have to be evaluated together, and it puts additional constraints on us.
So what about per session? How do we balance sessions? Well, it's a mesh. Like the example we looked at earlier, all clients are connecting to all servers. This has a lot of negative consequences as we start scaling to hundreds or even thousands of instances. In particular, we waste a lot of resources. So there's the inherent cost of a session. Then on top of that, we have to do health checking for each of those sessions to make sure that we don't select an unhealthy one and compromise success rate. And then what makes matters worse is that each load balancer has to discover these unhealthy nodes independently. There's no isolation between them. And a more subtle point here is that because these balancers compare load relative to other instances, if we don't have enough live or active requests, the load comparisons are ineffective. Another way to phrase that is, with low concurrency, when we pick two, it's likely that the two will not have any outstanding requests, so the load comparisons between them will be a no-op, and we effectively degrade to random selection. So this naturally led us to the question of how can we reduce the number of sessions without drastically changing our architecture or incurring any expensive coordination. And our first attempt at a solution here was something that we called random aperture. And random aperture is just to find a random window over which the load balancers can dispatch requests. And this allowed us to implement it in a simple way without any coordination. The aperture window sizing was also dynamic. So there's a simple feedback controller within each load balancer that allowed it to match the window size to the concurrency of a client. And this addresses a lot of the issues that we talked about earlier with low concurrency. So given the same service topology that we looked at earlier, random aperture might look something like this. So we have service A that converge on an aperture size of 3. And the idea here is that service A is receiving uniform load. So each load balancer within service A is converging on the same aperture size. And again, this solves a lot of the problems that we mentioned earlier. We have fewer connections. We have more concurrency across any given connection. And we have better isolation between particular failing instances in service B. There is one somewhat obvious problem here. Can anyone spot it? 5. Yeah, that's right. So we've created hot and cold spots on service B. So as the gentleman said over here, 5 has no sessions, and thus it has no requests being dispatched to it. And instance 1, in contrast, has 3 sessions. And it's hard to really appreciate the magnitude of this problem until we actually see the effects of it at scale. So this is what this looks like when we tested random aperture in production. So what are we looking at here? We see that we have, we're looking at a time series graph, RPC over time, RPS over time, and then we have this inflection point where the clients that are calling the service upgraded to random aperture. And then we see sort of chaos is ensuing. even here, we see that some instances within this graph are receiving no traffic, while others are receiving over 400 requests per second. And then the effects of this just make it really hard and impossible for operators to reason about aggregate capacity, overload scenarios, and it just results in really poor utilization. There was one interesting data point that came out of here, though. We see that there's this sort of banding effect where servers are concentrating around these visual bands. Fortunately, because random is statistical, we have all the statistical tools at our disposal to reason about this. And it turns out that the random process we use to select sessions that we put into apertures can be closely modeled by a binomial distribution. We can minimize this banding by tuning the binomial distribution, but we can never really eliminate it until we go back to fully open apertures. So armed with this knowledge, we decided it would be a good idea to tell our service owners and operators to start plugging into Wolfram Alpha and configure their random apertures. And in retrospect, this was a terrible idea. And not because it doesn't work. So here's that same service going from vanilla random aperture to a well-configured random aperture. And what we see here is much better load concentration. We still have a wider band than vanilla P2C. But the core issue here is that if we were to push this configuration burden on our service owners, this is configuration that will go stale as soon as the system changes. And one of the core tenets of our team is to actually ship products that work for 90% of our users out of the box without requiring them to do complex configuration. And this violated that. It wasn't something that we were willing to scale across our org. So this led us to the question of how can we improve Aperture? Namely, how can we make it more fair? How can we make it less config heavy? And a key piece of insight that moved us closer to a solution was moving to a ring topology. So these are the same services we've been looking at, service A and service B, except now they're mapped to rings, uniformly distributed on those rings. So this draws a lot of inspiration from consistent hashing. If you're familiar with that, the key difference here is that instead of actually using a hashing algorithm to map instances to rings, we're doing so based on a little bit of metadata, which allows us to spread the nodes out uniformly on the ring. So let's see how that works. So here's the ring for service A. And service A, again, in this context, is dispatching requests to service B. So in the ring model, we say that service A is the peer ring because the instances on service A are acting in concert to dispatch requests. And this ring is conceptual, actually. Each instance on the ring doesn't have to construct the entire ring. It only needs to know about its coordinate on the ring. And we do so by passing a little bit of metadata to each instance. So each instance needs a unique ID. It's usually an integer that we can order. And it needs to know how many other peers there are. So how many others like it there are. With these two pieces of data, we can actually compute the position of any respective instance such that they're all equidistant on this ring. And I do want to highlight that the domain here is 0, 1. It doesn't have to be 0, 1 in our implementation. We're using that. It just, the important piece here is that the domain is shared between the various rings. And we'll see how we use that later on. So this is service B on the same ring model. And in this context, we call it the destination ring because it's receiving load. And each peer ring computes this destination ring. And it has all the information to compute this destination ring from the service discovery system. So it has all the instances. And each instance, again, carries a little bit of metadata, like a unique ID, to be able to map them to the ring uniformly and deterministically. And because they do, this ring also shares the domain 0, 1, we can actually compose the two rings. And the resulting ring looks like this. And what this does is it actually gives us a sense of proximity between the two rings, and we can derive an ordering over which we can open our apertures. So for example, instance 0 in this case derives the ordering 0, 1, 2, 3, 4, 5, 6. Instance 1 derives the ordering 3, 4, 5, 6, 0, 1, 2, and so on. So now that we have those orderings, again, we can open up our aperture over them. So we've converged hypothetically on an aperture of size 3, and this gives us the histogram on the right-hand side. So this looks a lot better than where we were before. Again, instance 5 now has sessions. They all have sessions, so there's no extreme hot and cold spots. But we still see that 5 has, for example, 2 sessions, and 0 has 2 sessions, while the others have 1. And this may seem innocuous, but actually, depending on how many requests are dispatched over a session, it can be quite pronounced. So here we introduce a new service C onto the same ring domain. And C is dispatching requests to B as well. And we see the problem highlighted even worse. So visually, we see that there's now crowding on the ring. So if we look at the distribution on the left-hand side, we see hot and cold spots that are much worse. So 5 is represented 4 times across the apertures, and 1 is only represented twice. So in general, the problem just gets a lot worse as you start composing more and more service rings together.
All right, so how can we address this problem of off by ones? We did this by moving to a continuous coordinate system. So instead of mapping one instance of a client or server to a point on the ring, we give it a slice of the ring. And that's how this new representation looks. So for example, you can see that client 0 has a slice that overlaps with the service B's instances 0, 1, and 2. So looking at this new representation, we can kind of see why we had off by 1 issues before. And it's simply because service B doesn't have enough instances to be equally divisible by service A. In this new representation, what we can do is just simply share nodes. And we share them unequally possibly or not at all. This allows us to even out our request distribution, but it comes at the cost of an extra connection at these boundary nodes. But this isn't a problem that we really have to worry about, as you'll see in future slides. So how do we do our selection at this point? So we've moved from having discrete backends that are assigned to us to now having just ranges and to work with. So we do it very similar to what we did before, but instead we just pick 2 points uniformly on our client's range, and then they get mapped back to discrete backends. This strategy inherently respects the asymmetric sharing that may occur on, for example, instance 2 and 4 in this case. So let's walk through the code again a little bit. So this is the same pick2 code that we saw previously, but modified for deterministic aperture. We'll walk through it line by line just so we can highlight the differences. So at the top, we again have our selection phase. Our inputs are now the offset and width, which Ruben talked about in previous slides. And that defines this pink slice at the bottom, just where it starts and where it ends. From there, we pick 2 random points, which are the lines on 2 and 3. And then they get assigned back to discrete nodes. So how do we expect pick2 to work? It works the same as previously. It picks 2 points at random and just tries to make, or it just does make sure that we don't accidentally pick the same node twice. So then we move down to the next phase, which is evaluating their load. Since we now partially own nodes, we need to take that into account when evaluating load. And this is where the separation of concerns between selection and evaluation really enable us in this case. So again, we assume status is open, and we then fall to line 18s and 19, where we simply compute the weights that are assigned to each node in our aperture slice. And then we move down to line 22, where we just simply weight them inversely proportional to how much of them we own. So it's important to make sure that this works with multiple services talking to the same destination. As we saw before, we could get stacking. But in this case, since each service is evenly loading the destination ring, the sum of their loads will be equal. So composition works very well in this case. Let's recap what the continuous coordinate model has bought us. So we were able to regain the fair request distribution that we had in P2C. So since we're deterministically and evenly slicing up the backends, we can ensure that they're all picked the same uniform distribution of times. So, and it's distributed. So all we needed was that metadata that Ruben talked about, the aperture slice that defines our aperture slice. That's the only coordination that's going on between clients. So we don't have to have any heavyweight coordination models or coordination infrastructure to keep this even distribution. So last and not least, we can have a lot fewer sessions than we can with P2C and even random aperture. So since we can deterministically partition our backends, we no longer have to play the statistical games that we did with random aperture. And it doesn't come with a trade-off of more sessions to get a more fair request distribution.
So as Bryce mentioned, we do get fewer sessions. We haven't explicitly said how many, but what's happening here is, in general, it's 1 over n, where n is the number of peers in our peer ring. So we just equally distribute the domain. But it doesn't have to be fixed. We can grow or shrink our aperture so long as we do full rotations around the destination ring. So in this example, we have service A, again, dispatching request to service B, but we have this additional constraint where we want to have service A talk to at least 4 instances of service B. And the way that we do that is we do 2 full rotations around service B. And that essentially leaves us with each instance of service A talking to 4 2/3 of B. Another important consideration when we were designing this is how do we make it resilient? And a lot of this feedback came from customers, and some of it just came inherently when we were working through some of the ideas. But here's an example where we want to think about how do we have the smallest amount of changes to our rings when we don't need how can we avoid changes to our rings when we don't need them? So in this particular example, what we're doing is we're using a small heuristic where we decide, where we look at the instance IDs rather than the number of instances. So in this case, the tail of our ring is still intact. So we infer that our ring size is going to be 18, and then we put the peer instances in their final locations rather than shifting things around unduly. So in this example, so we actually use this heuristic extensively when we're doing rolling restarts. Another strategy that we use to minimize disruption is that we coalesce changes to both the destination and the peer ring. So on the right-hand side, you'll see these transactions, and some of them can be happening because nodes become transiently unavailable and then they come back, and we actually want to avoid flushing those changes to the ring. Sometimes this can also be stemming from a flappy service discovery system. So if any of you have worked with Zookeeper, you'll know that sometimes it's psychopathic, and it'll give you just updates that, for example, it'll have a GC pause or something, and it'll give you data that you can't really trust. So to not flush that directly into our ring coordinate system, we implemented this coalescing of updates that allows us to buffer these changes and process them and then flush them after some window. Another common failure mode that we try to avoid is thundering herd. So we do so by pseudo-randomizing the view of the destination ring for each peer ring to avoid any synchronization. So here again, we're looking at a third service, service C, that's talking to service B, and it has its own unique view of service B, such that if any instances in its aperture go down, if any instances in B go down, we don't route around it and cause concentration of load on service B. And we do this with using a murmur hash. And we use a murmur hash because it gives us this really nice property where we don't get any collisions on 32-bit inputs.
All right, we've told you a lot of the theory about it, showed you some diagrams, and now we're going to tell you about some production results. So we've been able to deploy this at scale at Twitter, and right now it's positioned as our default load balancer for services. So let's look at how a rollout worked for a well-configured random aperture service. So we're going to break this down into 3 different parts. As you can see, there's 3 pretty clear sections of this data. And this data is, again, just the RPS per backend server. So if you look at the left, you'll see the telltale signs of random aperture, namely the banding. You'll see high bands and low bands, and you'll see they kind of stay in the same position. And again, this is tough for service owners because it's hard to reason about capacity. Then in the middle, you'll see a lot of noise. This is noise due to the transition. So as we're starting to reorder our how the clients talk to the backends, you'll see some stacking. It's important to note that this is only when you're transitioning to deterministic aperture. This is not every redeployment, every restart. This is a one-time cost. And then afterwards, you see the promised land of a nice tight load distribution, which is very similar to what we get with P2C. You'll see that the noise in there is all just instances bumping up and down. It's not long-term correlation, so we're not really wasting any resource there. So this is the same data, just kind of turned into a relative standard deviation. As you can see, we're not doing too bad with random aperture, just below 0.2. But after the transition, we're able to drop that significantly. In fact, we've dropped it by 78%. So let's look at the number of connections. Random aperture was developed so that we could reduce the number of connections in scale clusters. But we can see that we've been able to reduce it by even more by using this deterministic aperture implementation. So before the rollout, this cluster talking to the backend cluster had 280,000 connections roughly, and we were able to drop it to 25,000, or a savings of about 91%. We also had a lot of second order results. So we were able to see a 20 to 25% reduction in CPU time. Garbage collection times were cut in half, 75% fewer failures, and significant savings in P999 latencies. So that's not the only cluster that migrated, obviously, and so here's some more data. This is a cluster going from P2C to deterministic aperture. It has 2 traces. You'll see the blue line, which is the normalized number of connections. It's steady, 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 and after the transition, basically falls into the baseline. I don't remember the number, but it was something like a 98% savings in connection count. You'll also see an orange trace on this. This orange trace is more interesting. This is the count of requests that were retried automatically by Finagle through the various mechanisms it has to detect requests that were failed due to broken pipes, stuff like that. Basically failures that it found too late but could auto-retry. You'll see that there's some noise, but then after the transition, it's dropped significantly. This is due to the better isolation we get, as Ruben noted earlier. So since every client isn't talking to every backend server in the cluster, and this cluster is on the order of 5,000 nodes, there's going to be some failing nodes there. And not every single client has to figure that out independently. So there are some limitations of deterministic aperture. Some of these are not even unique to deterministic aperture, but actually properties of subsetting load balancers in general. So if your client cluster has an uneven workload, likely it's going to send unequal workloads to its back end. And this will again cause stacking, and you'll find yourself back in this banding situation. This can happen in the steady state, meaning clients just throughout their whole lifetime receive different amounts of load, or it can be bursty traffic situations. One example we ran into was a service was maintaining an internal cache that it would flush on an interval, and then once it would flush it, it would repopulate, and that would give it a huge burst of traffic, and that would overwhelm back-end instances. So it's also not done. We have some future work to do. In the diagrams we've shown you so far, every single node has been the same width. But that doesn't need to be the case. Now that we've moved to the continuous coordinate model, we can account for things like different capacities. So as anybody who's scheduled a cluster of instances in an environment that has more than one type of hardware knows, you ask for 100 instances, each with 4 cores, but not, some cores are more equal than others. So this will allow us to encode that information into our peering system, and what that results in is some members are simply widened and some can be contracted, and that allows us to encode that information in the ring. Our picking algorithms automatically will adapt to that. They pick in the slice. They don't care how wide the back-end slices are. They will just simply remap. So we told you a lot of the fun stuff, and as a good talk does, it tells you how everything went really well. But we also wanted to include how it wasn't all roses. About a year ago, I decided to quit writing bugs, but unfortunately, that was after we did a lot of this work. So we'll start with some of the fun stuff that happened. So here's a situation where a cluster was doing a redeploy, and it turns out there was some of that noise that we talked about earlier during the redeploy. You'll see a couple spots, so you'll see a lot of noise and then a pause, a lot of noise and a pause. That was them pausing the deployment of the cluster. Their SREs were, oh my goodness, what's going on? Call CSL. And then it would just stay. They're like, okay, let's try a few more nodes. And it would rattle the diagram a bit, and then pause it and stay. And eventually they finished the deployment, and everything went back to beautiful deterministic aperture tightness. So what happened here? What happened is that during the deployment, instances, or high number instances, thought that they needed to wrap themselves around the ring. Basically, we got a ring overflow. And this goes back to the heuristic that Ruben talked about earlier, where instead of simply counting the number of nodes, we now pick the highest number node. So in this specific example, we're just trying to show that instance 1 was being restarted, so the ring contracted itself, changed its domain, but instance 3 thought it was, oh, I'm the 4th instance in a set of 3. Wonderful. I will go ahead and take this slot, which happens to clobber all the nodes that instance 0 is assigned to.
So here's another actually interesting failure mode that we ran into as we were developing this. We talked about this being light coordination, and it is very much so, but what happens when this light coordination that we're pushing through the system, this metadata, we fumble it. So in this particular case, we were passing the unique IDs through the system and even the size information through the system, and we had a race condition in which some clients were dropping the data, and they were sort of dropping the updates, and only subsequent updates would they actually converge on the rest of the cluster. So we'd get these weird sort of Winamp effects, I call them. And they'd be very sporadic. We knew they were sort of correlated with updates. So tracking this down, we were looking at our service discovery system. Is that sort of dropping data, or is that inconsistent?
Zookeeper.
Yeah, Zookeeper. That's right. And what that looked like here is that you have instance 1 that thought that it only had 3 peers. Everyone else thought, okay, there's 4 peers. and then you have this mismatch in how we're mapping the rings. And we did end up tracking the race condition. It was a bug in our code, and we were able to sort of resolve that issue. So we'd be remiss to not say that this is the work of many. Lots of people have contributed to this idea over time and helped us shape it and evolve it into what it is today. Like we mentioned earlier, Finagle is an open source project. So over 90% of what we showed here is available for you guys to dig into and actually look at the details. And finally, we're hiring. We're hiring all over the place, including Singapore. So if you haven't talked to us or other folks from Twitter here and you're interested, please do so. And I think we have plenty of time for questions.
Where and how do you calculate the load of the nodes? Is it in the clients?
Yeah, it's a good question. Yeah, so today we do it all client-side. Again, like Bryce was saying, load is sort of this generic concept that we can roll in all sorts of data into. So eventually, and we didn't talk about this in future work, but we've definitely discussed it on our team where we can get a higher fidelity metric by sampling load on the server and then combining that with the client's understanding of load. But today it is all client-side.
And how do you deal with some requests being more expensive than others? Do clients kind of have a model for that?
Yeah, that's a good question.
Latency?
Yep. So the way that we do that is we do least loaded. So clients, as soon as they dispatch a request, they increment a counter, and they only decrement that counter when the request comes back. So it inherently follows latency.
And the second question would be doing canaries on the backends, but I guess you have the flexi ring for that. So if I want to have like only a small fraction of traffic to like a test node, I would give it a smaller part of the ring.
Yeah, that's a good question.
So that is actually a pretty tough challenge for us in our environment because we have a very small cluster often talking to these big ones. And right now, they end up with just, they degrade close to the P2C case, or they change the load balancer implementation temporarily. Since canaries don't have a ton of traffic, usually it's not a big deal. But it is something we need to address in the future.
Thank you. Those were great questions.
I have two questions. The first one is, if some node dies from the ring, or if you want to add a new node, how does that affect the metadata of other nodes? Because are you trying to keep it uniformly divided?
Yep.
And how the requests are forwarded to the upstream when this like scaling is happening?
Yeah. So we definitely rely on things becoming eventually consistent. We don't need heavy synchronization. And again, we're relying on the service discovery system to converge all the clients on the same metadata. And in between those updates, we do get some noise. The ring model doesn't necessarily add any additional noise there. So because we are mapping things deterministically, and we do have things like the peer size heuristic that we talked about, where we try to place things where they're going to be. Strategies like that help us combat shifting things too often. And what was your second question?
So second question is, so in your load balancer, how do you like check whether the upstream is healthy or not?
Yeah.
We do it one of two ways. So we just collect data as one way. So if we see failures, we have circuit breakers to detect that. That's the passive way. We use a custom protocol which has health checks, more or less just pings. That doesn't give you information about the application health, but it does give you information about is the JVM still running, is the network good. So we rely on a few mechanisms for that.
Okay.
Thank you.
Thank you.
Do you have any detection for query of death, or do you limit the amount of ring changes you allow over a period of time?
So query of death meaning a client sends a bad request?
A single client killing all 3 peers from the example, and then the ring changes because all backends go unhealthy, then it's killing the next 3. And
yeah. Yeah.
So we don't, when a node goes down, We don't shrink the ring unless it was the largest node. We only shrink from the head of the ring, so to speak. So in those diagrams, say client 0 murders its backend instances 1, 2, and 3. It'll go down. Client 0 will have nobody to talk to, but the other nodes will remain healthy. In general, poison pills in our architecture are, we absorb them fairly well in that regard, just because our clusters are pretty big. We get a lot of dispersion. I mean, if we have a bad request that is targeting, or lots of them, we can have problems, but I think that's true of every single load balancing strategy you could think of.
Thank you.
Thank you.
Thank you. Great, thank you all.